enough. How are you doing? Yeah, welcome to Baku. I hope you enjoy this beautiful city, hospitality, and this amazing venue. I know it's like many of you are jet lagged, so we're starting in a very soft way. Yes, if you need anything, you can always find our volunteers well in blue shirts. You can find our staff wearing black shirts. We all want to give you a very warm welcome and the best experience here in Baku at the ICPC World Finals. So I have a few announcements. First announcement, all the participants, all the students, you should have received your ChatGPT Pro license. If you haven't done so, please come and talk to OpenAI booth and they will help you with a license. Another short announcement is that we're having an Sora Jam running all these days. It's an AI-enhanced videos, like you can create your videos and like fun videos using AI, and we'll be announcing the winners at the end, and you'll have a chance to win a special prize. So if you are not yet part of this AI video Sora Jam, you can also come to the OpenAI booth, scan the QR code and join the game. It will be very fun. So I encourage everyone to join. I'm going to create my video today as well. And yeah, anything else, come and talk to us, find the volunteers for any questions, okay? And now it's very exciting. First of all, I would like to introduce and call on stage Jelani Nelson. Jelani, please. Jelani is our ICPC Alumni Chair, and Jelani was with us for the past few years. Jelani was a contestant and currently a coach of the University of UC Berkeley, but he's also the ICPC Foundation Alumni Chair, and Jelani has been inviting some really amazing speakers to us so all these years. So Jelani, maybe can I ask you to say a couple of words?
Yeah, I guess about being a contestant, I never was a very good one. So I went to MIT, and the team was very competitive there. So I never was actually on the team, but I served as a student coach, and now I'm a coach. But yeah, I guess a few years ago we thought there's so many people who come here who obviously are very interested in algorithms, and a lot of the if you think that like the standard tool set of which algorithms you need to succeed at ICPC, many of them were developed decades ago. For example, Bellman-Ford. Everyone in this room knows about Bellman-Ford, but it's about a 70-year-old algorithm. It was designed in the mid-50s, and algorithmists have been busy working on coming up with better algorithms since then. And today we're going to have such an improvement that's going to be presented to us by Jeremy Fineman, who developed such a better algorithm. The first improvement to general single source shortest paths since Bellman-Ford. So Jeremy is he's a professor and director of graduate studies and holds the Wagner Chair of Computer Science at Georgetown University. His main research interest is in algorithm design and analysis with a focus on data structures, parallel algorithms, memory efficient algorithms, and scheduling. He got his PhD at MIT in 2009. His advisor was Charles Leiserson. People know the book CLRS, so the L, Charles Leiserson, and he did a postdoc at CMU before starting at Georgetown. And he's going to talk to us about, again, the first improvements of Bellman-Ford for general weights, not integer weights, since 70 years ago. Thank you.
Thank you. All right. So I will just wait a moment while they get these slides put up there. There we go. All right. So thank you all for coming. Let me just go through a little bit of introduction. I'm sure all of you know the shortest path problem and Bellman-Ford algorithm, but I just want to get us all on the same page. So I am talking about the single source shortest path problem, where we have a directed graph drawn up there on the top with weights on the edges, and the weights can be arbitrary real numbers, both positive and negative. On the slides, all the numbers will be integers, but this would extend to general numbers. And you're given some source vertex, which is the green vertex S up there, and you would like to find the shortest paths from S to everybody else in the graph. So the paths would form a tree highlighted in yellow, and the distances I'm filling in on the inside of the vertices there would be the shortest path distances. I will write the expression distance from S to V using that notation to talk about the distances. Now for the talk, I'm going to be assuming that there's no negative weight cycles in the graph, because otherwise these shortest paths are not defined. But typically the application where you care about shortest paths with negative weights is really more about finding the cycle than figuring out what the weights of the paths are. So I'm going to be sweeping that aside, but this algorithm will also find a negative weight cycle if there is one in the graph. Okay, so this is the problem that I'd like to solve. Let me give you a little bit of background, but Jelani already summarized some of it as well. The classic solution, of course, is Bellman-Ford. I put up some pseudocode here, which I don't need to go through for all of you. Of course, just for a quick review, Bellman-Ford just goes through all the edges in whatever order you want and sees if you can get a better path by using that edge and extending it from the previous one. So in this case, you would see you've improved that distance. For this edge, there's no improvement. And for the third edge that I'll show here, that gives an improvement again. And you would just keep repeating this process until nothing changes. So what you probably learned in your undergraduate data structures or algorithms class is that this algorithm has at most n iterations, where n is the number of vertices, that it correctly computes the shortest path distances, and also shortest paths in general, which is exhibited directly by this algorithm, obey the triangle inequality. So the distance to some vertex v is less than the distance to u plus the weight of the edge from u to v. Okay, so I'll just refer to the triangle inequality in a couple places in the talk, but that falls directly the way the algorithm goes, because otherwise you would still be executing. All right, so that's the standard solution. And it turns out that for the setting of real weights, this was pretty much the state of the art until this work that I'm talking about. So this algorithm runs in mn time, where m is the number of n is the number of vertices and m is the number of edges. I'm used to calling it the Bellman-Ford algorithm because Charles Lyserson was my advisor, and that's what the textbook calls it. But this is usually attributed to several other people, including Moore and Schimble, depending on which book you're using. All of these people develop basically the same algorithm at the same time. Okay, and if we're restricting our attention to non-negative numbers, of course, Dijkstra's algorithm can be used, and the sort of standard solution that most of us would be familiar with there uses Fibonacci heaps and runs in m plus n log n time. This has been improved a little bit more recently, but I'm not going to talk about that improvement. One of the reasons I'm not going to be talking about it is I'm going to be ignoring all log factors throughout the talk. So this is a notation maybe few of you have seen before, but probably most haven't. This O tilde just means I don't care about logs. So when I refer to something like Dijkstra's algorithm, I would just write O tilde of m. So that's the state of the art for real numbers. What most of you probably haven't seen is that for the case of integers, there's been a long line of work trying to improve the running times of these algorithms. And I'm just going to put up the last one, which was a couple of years ago. You can get nearly linear time to solve the single source shortest path with negative weights, as long as everything is restricted to be an integer. Now there's two different flavors of approaches here. The ones in blue are sort of the combinatorial approaches, which would look like the normal graph algorithms that you're used to. The ones in black are the ones that use sort of interior point method and gradient descent-like approaches, so more algebraic things. I'm only going to be using combinatorial approaches in the talk, so you don't need to worry about that. And at their heart, all of these algorithms do some sort of scaling where you're sort of releasing one bit of the integers in each round of the algorithm, and they're kind of just getting an approximation in the end. It's just that each iteration gets you closer and closer to the right answer, and eventually, since they're integers, you can just round off any remainder that you have, and you're going to have the right integer answer because the nearest integer is the right one. This does not work when you extend to real numbers because you don't have a finite precision to work with. Okay, so that's sort of the state of the art for integers. There's also other types of special cases, which I'm not going to put up. But for this work, the goal is to beat the Bellman-Ford for reals. And I beat it by a little bit. So we can get from m times n down to m times n to the 8/9. Okay. So. Okay, so I'll give you a little bit of an idea of sort of the overview of the algorithm and how it works. There's a lot of details I'm not going to be filling in. Most of the cleverness, I think, was in sort of structuring the approach, so hopefully I get that across at least. If you do have sort of clarifying questions as I'm going, I'm not quite sure it'll work well in this room, but I am happy if you just want to shout out a question. Shout out a question. In a way that doesn't change what the actual shortest paths are. Okay, and it turns out that if you just assign a number to each vertex, so I'm using phi for the number, and I just changed the weights in the entire graph to be whatever the original weight was, plus the price at the starting point, minus the price at the ending point. This is, you know, a way to define the weights. So let me do this by example. Here's a path here. If I add up the weights of all the edges on the path, I just get 2. And I'll assign some price function that I pulled out of thin air to adjust each of the vertices. And then I can reweight the graph according to that definition up top. What's written on the edges there is the new weights that I would get using that price function. So you can see for each one, I'm taking the original weight plus the price of the starting point minus the price of the ending point. Okay, now if I add up the weights across the entire path, things start to cancel out. So we have this nice telescoping series, and we are left with the original weight of the path plus the price at the start minus the price at the end. So importantly, the only thing that's adjusting to weight is the 2 endpoints, which means that every path between the same 2 endpoints would be adjusted in exactly the same way. So if you do reweighting using price functions like this, shortest paths between a particular pair remain shortest paths between that pair. The actual weight of the path changes a bit, but it's still the shortest path. Okay, so this is one of the tools we're going to be using. All of the integer approaches apply these price functions in various ways as well. This is not new. Okay. Now, Johnson had the observation that if we want to force the new weights to be non-negative, that's equivalent to setting the price, the target, to be less than the price of the starting point minus the weight of the edge. You get that just by setting that greater than or equal to 0 and moving things around. That is the triangle inequality. So any price function that satisfies the triangle inequality will give you non-negative weight edges, right? So Johnson's technique was to just use distances as the price function because distances obey the triangle inequality. So if this is my entire graph consists of that path there, you would add a dummy source node with new edges to every vertex with a weight of 0, compute the shortest path distances from that source, that's your price function, and then reweight the graph according to that price function. Okay, and as you can see in this example, these are non-negative, and this will always be the case. Okay, so this is what Johnson's algorithm does. This is going to be the first tool that we're going to be applying. Okay, now the only reason for the dummy source is just to make sure that everything is reachable, because otherwise you would have some infinities in there and you wouldn't be getting the guarantee that we want. So Johnson's algorithm just applies Bellman-Ford to compute that shortest path distance. Bellman-Ford runs in mn time. So far, that's exactly the problem we wanted to solve, so we don't get any improvement there. So we're going to have to apply this in more careful ways that can be done faster. Okay, so let me set up a little bit of terminology. There's going to be a couple points in the talk where I need some terminology. So I want to talk here about eliminating negative vertices. So I have an example graph up top there. I'm going to be talking about negative edges, and that just refers to any edge that has negative weight at the start of the algorithm. These I'll be drawing in red, so all the red edges up there are the negative edges. A negative vertex is a vertex that has any negative outgoing edges. Again, the ones drawn in red in the picture. And I say that a price function eliminates a negative vertex if after reweighting the graph with that price function, the weights of all the outgoing edges have become positive. So if I reweighted the graph to produce the one on the right, that yellow vertex towards the top right of the graph no longer has any negative weight edges leaving it, so that vertex has been eliminated. Okay, so that's going to be our goal, to eliminate the negative vertices. Now when we do this, we want to do it in some nice monotonic way. So I'm also going to require that any weights that were positive when we started stay positive when we reweight the graph. We're going to get this for free with the subroutines we're running, but it is important that you have this feature. Okay, so Johnson's algorithm that I described on the previous slide would eliminate all of the negative edges in just one go by running Bellman-Ford. But we're not going to try to be that aggressive about it. Instead, we're going to settle for just eliminating some of the negative vertices. Okay, and as long as we can do better than order m time per vertex that we eliminate, we're going to beat m times n, right? Because there's only n vertices to eliminate in total. Okay, so that's all we're shooting for, eliminate some good number of negative vertices faster than n per vertex. Okay, so now I can give you the main result. So throughout the talk, I'm going to use k to talk about the number of negative vertices. And the main theorem is that there is an algorithm that eliminates k to the 1/3 negative vertices, and it does so in time that is the size of the graph times k to the 2/9. Now the important feature about this is that's less than m per vertex. So if you plugged in k is equal to n, this would give you a savings of n to the 1/9 per vertex that you've eliminated. So that's where the final running time comes from. So you would just take this algorithm specified by this main theorem and repeat it until you've eliminated everything, and then the algorithm if you look at the yellow path along the top, that is a 3-hop path. And if you look at that blue path along the bottom, that is a 1-hop path, because that's the number of negative edges along it. Now you can extend notions of distance to talk about distance restricted to paths that use that many hops. So the 2-hop distance here, for instance, would force me to use at most 2 negative edges. Well, then I'd have to take the blue path along the bottom, which would have a length of 9. Right? If I allow you to use 3 hops, the distance would be -1 using the yellow path across the top. Okay, now it is very easy to construct an algorithm that will compute h-hop distances from a single source in time h times the size of the graph. Some of you probably already know how to do this, but all you do is you alternate between rounds where you run Bellman forward on all the negative weight edges, and then you do a full execution of Dijkstra's on all the positive weight edges. And you repeat this h times, and this will give you the h-hop distances. Okay, so this is the second subroutine I'm going to be using, is these hop-limited shortest paths. All right. Now, I'll just point out that if there are only k negative vertices in the graph, you know that you only need k hops, so you can solve single source shortest paths in k times m time. Okay, now we're going to be using this in various places and try to beat this, but that's what we have as a building block. Okay, so let's just see what happens if we tried to use hop-limited shortest paths to do something like Johnson's algorithm on a quick example. And I'm going to use 1-hop distances here. So, right, so let's say I add a dummy source, put some edges with weights of 0 to everybody in the graph, and then I compute the 1-hop distances and set that to my price. So if I didn't make any mistakes, the blue numbers down there should be the 1-hop distances from the source to each vertex. And then I reweight the graph. Okay, so one thing that we'll notice immediately is there's still a negative edge, right? I didn't get rid of that one. In fact, it got more negative than it was before. So I have no guarantee that it improved in any way. So the bad news is that when you do this hop-limiting truncation of the execution, you don't guarantee the triangle inequality on the part where you're truncating, which is the negative edges. But the good news is that you do still get the triangle inequality on the non-negative weight edges. So as long as we're using this as a subroutine, we will never introduce new negative edges along the way. We just have to worry about whether we get rid of any of them. Okay, so we're going to be trying to do things like this as we go. If you have any questions as I'm going, again, feel free to just shout out. This might not be as much detail as you want when it comes down to it. But, all right, so let me give you a high-level overview again. So our goal is to reweight the graph in a way that eliminates some good number of the negative vertices. We want to do this in a way without introducing more. So the general approach is going to be to start by finding a subset of the negative vertices that for whatever reason is easier to deal with. Okay, so perhaps for the pictorial example here, I decide that those 2 yellow vertices are sort of easier to work with. Okay, so then the next thing I'm going to do is remove all the other negative edges that are not the ones leaving these vertices. So I'll drop those other edges from the graph. So now I have a graph with just those 2 yellow negative vertices. And then we're going to try to eliminate those. Okay, so we're going to do some other process to eliminate those. And this involves reweighting the graph. And now we have this subgraph of the original graph that has no negative weight edges in it. Okay, but this is a subgraph of the original graph, so I have to solve the problem on the original graph by adding back in the edges that I removed in the first place. And those edges can have weights that are really anything, so they might still be negative, or I might have gotten lucky and some of them might have become positive, I don't know. But those could still be negative. I add them back in, and now I have the reweighted version of the original graph, where I have eliminated the 2 yellow vertices, but the other negative vertices still remain. Okay, so there's now just 2. Okay, so that's the general strategy we want to follow. Of course, a natural question is, what is a good subset? What's something that's sort of easy to find and easy to work with and eliminate some things? Okay. So let me give you the easy case first. I claim that something that I'll call an independent set is easy to deal with. So what do I mean by an independent set? So an independent set is a set of negative vertices where the shortest path distances in both directions are not negative. And I can restrict my attention here to one hop shortest paths, something that I can compute easily. So this is an example of a graph, which would be, again, we'd be looking at this as a subgraph of the original graph. But here's an example of the graph where the negative vertices do not have any negative weight paths between them. Okay, so in this case, if I'm promised that my graph looks like this, that they're independent, then I claim that you can eliminate all the negative vertices very quickly, just in linear time. Okay, and this, again, is something that's not difficult. You could probably solve this offline as an exercise on your own, but I'll just tell you how to do it. We're going to run Johnson's algorithm, add a source vertex and some extra edges there. And I want to compute the shortest path distance from the source to everybody, but it turns out I only need to go one hop. And once I go one hop distances, those are exactly the shortest path distances, and I can just truncate the algorithm. Now, why is that the case? Well, let's do this by example. Is there any reason I would need to take that path that goes through two negative vertices rather than, oh, something didn't appear there. My animations seem to have disappeared on me. Sorry, let me just get that going. Okay, so is there any reason I would need that yellow path instead of the blue path? Well, no, because I'm guaranteeing you that the distance from B to D is at least 0, so you may as well just go directly to D. Okay, so you never need more than one hop on your path, because you adding extra hops is just going to make it something that's at least 0. Okay, so if this is the case, I can do it in linear time, and this is a very easy case to deal with. So if we could always find an independent set, we would be done. Unfortunately, I don't know how to do that. Okay, so we're going to need some other option for doing something. And the other option is something that I defined for doing this work, which I'll call a remote subset. Okay, so I'm going to think about first the vertices that you can reach by negative weight paths that are limited to the number of hops that we're talking about. I call this the R-hop reach of a vertex. So if I'm going to focus on the vertex U on the left in my picture, the one hop reach of U would be that region that's highlighted in orange. These are the vertices I can get to with paths that have strictly negative weight. If I talk about the two hop reach, these are the things I can get to with paths of strictly negative weight that use at most 2 negative edges along the way. It's not guaranteed to be connected or anything like that, because I might have to pass through some other vertices along the way to actually form these paths. That vertex that's sort of missing in the middle, the weight of the path to get to that one is 0, so that's not considered in the reach because it's not strictly negative. Okay, so these are the things I can get to with R-hop negative paths. And I will say that a set of negative vertices is remote if, when I take the union of the R-hop reaches of all of the vertices I'm talking about, that union is only a 1 over R fraction of the entire graph. Okay, so that's what we're shooting for. So I don't have a great picture here, but if the gray region is the entire graph, the red vertices are the negative vertices, and the orange stuff is the stuff I can get to with negative paths using at most R hops from any of the red vertices. That should be a small fraction of the graph. That's what I'm shooting for. If that's the case, then I say that this is R remote. Okay, so this is a new definition here. The fact that the R talking about the number of hops and the R talking about the fraction of the graph that's reached is the same parameter was mostly just for simplicity. This is the only parameter in the algorithm is what we're going to tune R to be. You could make these different, and in fact some of the follow-up work has done that to try to exploit various things, but for the approach I'm doing in this talk, they may as well be the same. You don't get any advantage by making them different. All right, so again, it's R remote if the fraction of the graph I can reach by R hop paths with negative weight is at most a 1 over a fraction. So I claim that if we're given a graph where we have k hat negative vertices, and the negative vertices are indeed R remote, then you can solve single source shortest paths in that graph in time that is k hat times m, the size of the graph, but now over R. Okay, so just in comparison, if I did this naively using the mixed Bellman-Ford-Dijkstra's algorithm, it would have been the number of hops times the size of the graph. So we're improving this by an R factor. Now, I will not tell you how to do this unless we have time at the end, which we probably won't. But you might be able to figure out how to do this on your own. It's not super tricky. So this is one of the subroutines I'll be using. Just take for granted that we can achieve this. Okay, so intuitively, most of the interesting stuff for computing the shortest paths is going to happen in that orange region of the graph, right? Because that's where all the negative stuff lives. So most of the time, we're going to be doing work in that small region. Sometimes we might have to spill out a bit, but most of the time, we're in just a 1 over R fraction of the graph, so we get a 1 over R savings. Now, if we can solve single source shortest paths, then we can just run Johnson's algorithm to eliminate the negative vertices, because all you need to do is add a dummy source, solve single source shortest paths from that source, and then reweight according to that. So this is the only tool we need to eliminate a remote subset. Okay, now just to sort of get a little bit ahead and make these parameters a little more concrete here, k hat is going to end up being k to the 1/3. R is going to end up being k hat to the 1/3, which is k to the 1/9. So the savings we're going to get is this 1 over R factor, which is 1 over k to the 1/9 in the end. That's where it's all coming from. Oh, there's a question over there, yeah.
Excuse me.
Okay, thank you. Is this the real asymptotic for this deterministic algorithm for SSSP, or should this contain something like plus m, just because we actually probably need to consider every edge at least once?
Yeah, okay. So I'm making some implicit assumptions for simplifying things throughout. So one of the assumptions here is that k hat is bigger than R, because otherwise there's no reason to do this. You may as well do something else, yeah. There's a few places where like some of the running times actually do add together to aspects of cost, and I'm only showing the one that dominates when I do this. Yeah, good question. Yeah, so this part is deterministic. The overall algorithm is randomized, and I'll point out which are the randomized parts as we go. Okay, so let's put things together again. So the algorithm so far, we're going to search for a size k hat independent set or remote set, and then we're going to try to eliminate it. Okay, now finding these objects is the hard thing. Once you can find these, we know how to deal with it, right? I know how to deal with eliminating a remote set. I know how to deal with eliminating an independent set. And they're so hard that it's not even guaranteed to be possible. So here's an example graph where there is no non-trivial independent set, and there is no non-trivial remote set for R bigger than 1. So we can see that any pair of the negative vertices can reach each other with just 1 hop, and a negative weight 1 hop path, so they're not independent. And starting from any negative vertex, I can get to pretty much the entire graph on the right with a 1 hop negative weight path. Okay, so this looks like a bad graph. There's not much I'm going to be able to do to deal with this. So I have to work around it somehow. So what's the workaround? Well, we're going to have some extra steps to introduce in a little bit, but we're going to try to find either an independent set or something else that I'm not really going to tell you what it is. If we find the independent set, great. We know how to eliminate it, we're done. If we find the other thing, we're going to do some reweighting to make the other thing remote, and then once we've done that, we can reweight again to eliminate it. So we need this extra reweighting step to make this happen. Okay, so that's what I'd like to do. I'll fill in the box on the left in a little bit. So I just want to focus first on what it is that I need to, let's try to make some set of vertices remote and see sort of what goes wrong. Okay, so let's consider this situation here where I have the red vertices are the negative vertices. The orange region on the left is the stuff I can reach by negative weight paths, starting from those red vertices. And the stuff on the right is the stuff that would require, or doesn't have negative weight paths. The paths are non-negative to get to those. Okay, now I'd like to reweight this graph to move most of the stuff from the left to the right, so that only a small fraction of the graph remains on the left. Okay, so that's the goal. Okay, so let's look at what is the definition of the stuff on the right. Well, this is the stuff where the distance after reweighting from a red vertex to that vertex is non-negative. Right? Now, the distance after reweighting is the original distance plus the price of the starting point minus the price of the ending point. And the starting point is one of the negative vertices. Okay, this is tricky to deal with. I'm really not quite sure what to do here yet. But if I can somehow do this reweighting in a way that's going to force the prices of the negative vertices to stay zero, then we can simplify this to say that a vertex V is in this gray region on the right if and only if the price of V is less than the distance from every negative vertex to V. Okay, again, this is just algebra by flipping things around. Okay, so I would like to come up with a price function that sets the price of the negative vertices all to zero, and I'd like most of the other vertices to have a price that is less than the distance, the R-hop distance from negative vertices to that vertex. Okay, unfortunately, you can't do that. So here's a bad example graph. I'm showing just a subgraph here. So the red vertices are both vertices that have negative edges coming out of them, although the one on the right, you can't see it because it's not shown on my picture. So I'd like to set the price of the two red vertices to be zero, and I'd like to set the price of the vertex in the middle to be less than the shortest path distance from a red vertex, which means I'd be stuck doing something like this, 0 minus 8 and 0. And if I reweight the graph in this way, I'm going to create a negative weight edge, right? And we don't want to create negative weight edges as we're going. So this is bad. It looks like we can't do anything and we're stuck. But the observation is that this is not always going to happen. Okay, in fact, the only reason this happened is because this small little snippet of a path that I showed you has negative weight overall. So if this vertex V is on a negative weight path going from X to Y, I can't deal with it. I'm going to be stuck with it. But if it's on a positive weight path, I can do exactly this reweighting process, and I will be able to shift V to the right, make it so it's no longer in reach. Okay, so that's the idea. I'm not going to show you specifically what the reweighting is. I'm happy to answer questions afterwards or offline, but that's what we'd like to do. So the observation here is thinking about whether vertices are on negative weight paths is important. Okay, so now I can fill in a little more of the algorithm. We've added a first step here, where in this sort of first step pre-processing, I'm going to reweight the graph to try to make it so there are not many vertices between other pairs of vertices on negative weight paths. Okay, and that's really the only other component that we need. So I'm going to just define this a little bit more on the next couple of slides, and then I'll just give a summary of the algorithm. So this is really like the last thing we're doing here. Okay, so let me define what I mean by betweenness here. So I'm going to, rather than thinking about distances going directly from a starting point U to an ending point V, I'm going to think about distances where you're forced to take a path that goes through an intermediate vertex X. And I'm going to talk about the distance from U to V going through X. Now this is still going to be hop limited in the same ways. And I'm going to allow you to take R hops to get to X and then R hops to go from X to V. Okay, now you can define this in different ways and everything would still work. This is just a definition that I went with. Okay, so I have an example here. There's my graph. If I force you to go, if I want you to go from U to V, but you're forced to go through the vertex B, you'd have to take the path along the top. And that has a length of 8. If I force you to go through the vertex E, then you can take the path along the bottom, which would have a length of -6. And we can calculate this distance for every intermediate vertex that's possible, and I would get these 3 distances here. The distance through D is infinity because there's no way to get from U to D using, in my picture, the number of hops is 1, so using only 1 negative weight edge. So that's undefined, which would be infinity. Okay, so that's what it means to talk about a distance being forced to go through certain intermediate vertices. Okay, now what I care about is how many of these intermediate vertices are on negative weight paths. So in this picture, 5 of those numbers are negative. So the betweenness of U and V is 5. That's the number of vertices that are on negative weight paths between U and V. Okay, and I'd like to do some pre-processing that will drive this number down. Okay, so let me tell you how to do that. So let's start by considering just fixed endpoints U and V, and think about the distance through different intermediate vertices. And I claim that if the distance through X is more than the distance through V before I do any reweighting, then it's also going to be the same ordering after the reweighting. Now you can see this just by doing the algebra. I like to do things by pictures, but this falls directly out of the definitions of the distances. So for example, if that's my starting graph, those are the distances through every intermediate vertex, and then I sort them, let's say. So these are the sorted order of the distances through the vertices. Then I do some reweighting of the graph. It doesn't matter how I came up with this. And then I write the distances in that same order on the right. You can see that they're still in sorted order. Okay, this will always be the case. In fact, they've all changed by exactly the same amount. They all will increase by 6. Okay, because the only thing that affects this is what the prices of the endpoints are. So with that observation in mind, we can now come up with an algorithm to try to reduce the betweenness. Okay, so I claim that there's a pretty simple randomized algorithm that takes R squared m time, and it will reduce the betweenness down to a 1 over R fraction of all the vertices. So this is roughly how the algorithm would go. You sample some number of vertices, about R of them. In my picture, it's going to be 1, because 1 is a much easier number to deal with. And then you do any process you can think of to reweight the graph so that the distances, the R-hop distances to and from the sampled towards paths starting from that vertex, and then see the things you can reach with negative weight paths, and then set those prices to be exactly the negative weight or the negative distances. When you have more than one sample, it's a little bit harder, but it's still not that hard to do. This can be done in time that's R squared m. Okay, so and the picture on the right would be an example of this process after reweighting. All the distances from any vertex to E are not negative, and all the distances from E to any vertex are also non-negative. There can still be negative edges along the paths. It's just that the total length of the path is not negative at this point. Okay, so that's the algorithm. Now, why does this reduce the betweenness? Well, it really comes down to that ordering of through distances that I already put up there. So if I have one sampled vertex, it's pretty likely that that sampled vertex is basically in the middle of this sorted list. So when I perform the reweighting, well, its through distance is guaranteed to be at least 0 because every distance to get from anybody to it is at least 0, and to get from it to anybody else is at least 0. So all through distances that go through this sample are at least 0, which means everything below it in the list is also 0. Or sorry, also at least 0. Now this is true, we didn't even have to know what UNV was, right? This is true for every UNV that we can be talking about. Okay, now if I have more samples, so as I said, all the distances all the distances that were originally larger than distances of the samples will become non-negative. And if I sample roughly R things, I'm likely to sample something that is in the top 1 over R fraction of this list, which means that I'm going to be left with only a 1 over R fraction and be negative in the end. Okay, so that's the idea here, the sort of a quick summary of the analysis. All right, so that's what we have. Let me just summarize the algorithm to wrap up. So we're going to start by reducing the betweenness, which involves reweighting the graph. So the result here is that for every pair of vertices, at most a 1 over R fraction of the graph is on negative weight paths from U to V. Okay, then we're going to try to either find an independent set or some other object that I call a sandwich. If we get the independent set, we can fall into the easy case, but I'm focusing more on the hard case here. So the sandwich is just a particular pair of negative vertices that I want to be talking about that happen to have a lot of other negative vertices between them. So there's like a the graph where I've dropped all the other negative vertices except the sandwich. Has a pretty big sandwich or a pretty big independent set, and moreover that you can find those efficiently. Okay, the first 2 steps here use randomization. The 3 steps on the right do not. Okay, now if I put up the running times of each of these steps, the 2 expensive ones are the first one and the last one. So we promise that we can reduce the betweenness in something like R squared times M time. And I asserted that you can do single source shortest paths on a remote subset, and the number of negative vertices times the size of the graph over R. Number of negative vertices is going to be k to the 1/3, so we can do it in k to the 1/3 times M over R time. Okay, so we have this parameter R, we just want to tune to balance those 2 things. So you just set R to k to the 1/9, that's the best choice. Those 2 become equal, and we get the running time. All right, so that's my quick summary of the main ideas of the algorithm. So we see that you can solve single source shortest paths with real weights in slightly better than Bellman-Ford time. We already know this is not going to be the final answer. The main point was just to do anything that was better than Bellman-Ford by a polynomial factor. There are many natural directions for follow-up work. Of course, many people are working on improving the running time. I think it would also be nice to find a simpler algorithm, because this one still has several steps that are involved. I think in my version, each of the steps is kind of easy, but it's still a bunch of stuff that you're throwing together. This is unlikely to be practical in the near future, so it would be nice to get it there. But those would be the two main things worth doing. I think it's not worth really doing any implementation work yet on this, because we don't know what the final algorithm is, right? They expect that there will be many years of improvements before we settle on a good answer. All right, so I think I will stop there and maybe take some questions if we have time for that. Seems like no. All right, thank you. Can I use this one? Yeah. Okay, we had a question. It's right in front here.
Hi, thank you for your talk. So in one of the earlier slides, you gave us an example of a graph that didn't have an independent set, where there was this long chain of vertices.
Yeah.
So, okay, so yeah, in one of the earlier slides, there was a graph that didn't have an independent set. So then that means that that graph had a sandwich.
Then it will have a sandwich.
So
yeah.
then I guess the crust was the first and the last vertex.
So the first negative vertex
yeah.
and the last
Yeah.
negative vertex in that chain, everything else would be sandwiched between them, yeah.
Okay, yeah. Thank you.
Other questions? Is that a question over there? Or is...
Is there progress on making a deterministic algorithm that's faster than Bellman-Ford?
Yeah, that's a good question. Can you do this deterministically? I don't know of any progress on that. The randomization seemed like it was really necessary doing that between this reduction step, but it's possible that there will be a way to do it in the future. There hasn't been any progress yet.
With this randomization component, can you suggest some of the application area where we can apply this?
Apply which axis?
Randomized version of this algorithm.
Well, I mean, the algorithm's always going to get the right answer, right? This is a Las Vegas algorithm. It's going to give you the correct answer, just the running time is randomized. So as long as you're not in like a real-time system setting, then this would be perfectly reasonable to apply. Just what we have now, I don't think translates to something that will be faster in practice, because in practice, on real graphs, Bellman-Ford doesn't really take as bad as MN. Usually, you end up doing a bit better.
Thank you.
So there was some step with the divided by R factor in the single source shortest path. Can you give a hint on how to do this? Because I'm thinking about it, but there could still be M edges inside the subgraph.
Oh, so you're talking about eliminating the remote subset part? Yeah.
Yeah.
Yeah, so I can also show you my slides after I just disconnected.
Okay.
But yeah, you want to build a layer graph where you have one layer that sort of corresponds to, it would be easier if I just show you the slides.
Yeah,
But, I'll come find you afterwards.
Okay, okay.
All right, it seemed like only this side of the room had questions, but I don't see any others.
Hello, if anyone has any questions, can you please stand up and we'll get a microphone to you, please? If you have any questions, please stand up.
All right. I think we're... Oh, there's one over there. Yeah, Richard.
Does this work? Does this work? Can you hear me?
Yeah.
Okay. This is a bit of a, I mean, you mentioned a little bit of implementation. I know that this is a bit of a kind of orthogonal question, but let's say I want to test all these shortest path algorithms, right? Negative length, and I want to compare their performances. I know that there was like an early 90s Dymax data set, but that's kind of the most recent data set I could find. But is there a place where there are like very good benchmarks for these, especially negative length shortest path questions?
So the most code I've written in the past 15 years is probably like tens of lines of code. I don't know about that. Could not tell you, sorry. All right, I think that's all the questions. All right, thanks.